Last time we left off at this theorem, where the theorem, if you see the screen, we had defined the set G hat as the set of equivalence classes with respect to the relation induced by the subgroup H on the group G. So, AIH is an representation or a name for one equivalence class, and we defined an operation dot on this set G hat as the following: AIH dot AJH. So, this is an operation between two equivalence classes, which gives a third equivalence class AKH, and the definition is that AIAJ is an element of the equivalence class AKH. Okay, so that definition is precise, and now we want to show that G hat is a group. So, let us prove this. What are the conditions we require for a group? First is closure. That is by definition. Because you see that AIH dot AJH is by definition an element of G hat. So, it is certainly closed under the operation dot. That is not a surprise at all. Next, associativity. So, we have A1H dot A2H and then dot A3H. What is this element? So, you consider this. So, A1H dot A2H is A prime H, where by definition A1, A2 is in A prime H. And then A prime H dot A3H is A double prime H, where A prime A3 is in A double prime H. This is also by definition, correct? Now, put these two together. What is the relationship, or what is A double prime H in terms of A1, A2, A3? See, A1, A2 is in A prime H, and then A prime H, A prime A3 is in A double prime H. Okay. So, we can say why is this. So, A1, A2 is equal to A prime H1, all right, and A prime H1 times A3 is in A double prime H. So, this implies that A prime H1 A3 is in A double prime H, and clearly you can remove H1 from here. Let us just argue this little more carefully. So, we know that A prime A3 is in A double prime H. This implies A prime A3 H1 is in A double prime H. You agree with this? Because H1 is in subgroup H. Fine. This implies A prime H1 A3 is in A double prime H, because it is a commutative group, and A prime H1 is A1 A2. So, this is an equivalence class. This product is an equivalence class defined by the element A1 A2 A3. Whichever is the equivalence class in which A1 A2 A3 belongs to is this product. Now, associativity follows immediately, because you see that whether we do the operation on A1H and A2H first and then A3H, or we do A2H and then A3H first and then do A1H, that would give us A2, A3, A1 is in A double prime H. Now, by commutativity, A2, A3, A1 or A1, A2, A3, they are all in A double prime H. So, this completes the proof for associativity. Are you convinced? Is there a doubt in this? No. Okay. It's pretty straightforward. It's just that I went through the details because it is important to formally write down these details and verify that for a general group this does hold. Next, what is the next property? Commutativity. Okay. So, we have A1H dot A2H. This follows again almost immediately is A prime H, where A1, A2 is in A prime H. A2H dot A1H is A double prime H, where A2 A1 is in A double prime H, and these two together, A1 A2 and A2 A1 again by commutativity are the same elements. So, they both belong to the same equivalence class. So, these two equivalence classes are the same. Next, identity. What is the identity? H is the identity. Why is that? If you have A1H dot H, this is AH. Similarly, H dot AH, again that use commutativity, it is also AH. Inverse, that is the final property. So, what is the inverse of element AH? Obvious. What, at least you can guess it. What should be the element of AH? A inverse H. Let us verify that. Consider AH dot A inverse H. Let us say it is A prime H, then again by definition A inverse, which is identity, is in A prime H. And if identity is in A prime H, what does this mean? It means A prime H is H. That is the only equivalence class which contains the identity element, and that is the end of it. So, now we can see something quite interesting that has happened. We started with a group, we identified a subgroup of the group, and then we introduced the equivalence classes with respect to that subgroup. From the equivalence classes, we made a new set, and we defined a new operation which is somewhat related to the group operation, but not quite the same, because this is an operation over equivalence classes. And it turns out that that new set under that new operation is also a group. This is a very important process. So, it is given a name and a notation. So, let us define that. So, that new group G hat is written as G/H. This is the division sign, and in a certain sense this is what we are doing. We are dividing the group G by the subgroup H, because each equivalence classes is now represented by one element. So, there is a certain amount of division, that some kind of division that is happening, and that is the sense, or that is the reason why we write it this way, and that is why we call it quotienting. So, this slash is a quotienting operation, and we of course always need to quotient a group with a subgroup, and the result of quotienting is another group. Now, having seen this, let us get back to our motivating example. What we started with was this group of integers under addition. Then we identified a subgroup. There are many subgroups, but we let us say a set of even numbers, that is a subgroup. Now, if you quotient Z by the subgroup of even integers by this theorem that we just proved, we must get another group. What is that group? What is this group? Firstly, what are the equivalence classes we will get? One equivalence class will be 2Z itself. Other equivalence classes? Set of all odd numbers. 2Z is all even numbers, and there is exactly one more equivalence class which is all odd numbers. So, this group, the new group, will have just two elements. The 0 or the identity would be 2Z, and then there will be the other set of all odd number, that is the other element. So, what would be the operation on this new group? So, let us write the odd numbers as 2Z plus 1, that is the notation. 2Z is identity, what is the new operation, how does it look like? So, we only need to look at the definition of the new operation on 2Z plus 1 itself. Because this is 2Z is identity, anything that you operate 2Z with, you get back that element. So, what is 2Z plus 1? 2Z plus 1 dot 2Z plus 1. What is this? It is 2z, right? This is 2z. Everything else is defined already. So, that is it. This completely describes this group Z by 2z. Is this a familiar looking group? Let us define another group Z2, which is just two numbers 0 and 1, and the operation is addition modulo 2. So, for this operation addition modulo 2, 0 is the identity and 1 plus 1 is 0, and that is it. That completely describes this group. So, do you see similarity between Z2 and Z by 2z? What is the similarity? Yeah, it's isomorphic to Z2. Yes, we already have that notion now. This is isomorphic because except for the notation, that is, I am writing 0 by 2z and 1 by 2z plus 1, nothing else is different. The operation dot is really addition modulo 2. That is excellent. So, let me reiterate this. We started with group of integers, quotiented it with a subgroup. We got a new group, which is a familiar group. It is the set of integers modulo 2 under addition. Okay, we can do the same exercise. This is the first example. Let us say we can do a very similar example again. Let us say take another subgroup of Z. Sorry? Yeah, in general, any subgroup of Z will be of the form nz. That is all multiples of a number n. That is the general form of a subgroup of Z. It requires a little bit of working out, but you can do that on your own. So, what is Z by nz? You can work this out in a very similar fashion. What will be the equivalence classes for Z by nz? There will be nz itself will be an equivalence class. What are the other ones? nz plus 1, nz plus 2, nz plus 3 up to nz plus n minus 1. So, there will be exactly n equivalence classes. The group operation would be essentially addition modulo n. So, this is isomorphic to Z n, which is the set of numbers between 0 and n minus 1 under addition modulo n. So, that is the structure of the subgroup of the group that you obtain by quotienting a general subgroup from it, from Z. One interesting fact about this is none of these subgroups that we are getting are, or none of these groups we are getting are subgroups of Z. None of this Zn is a subgroup of Z, but by quotienting with subgroups of Z we are getting them. So, which basically is telling us that this quotienting by subgroups is creating new groups, and this is one very good way of creating new groups. So, let us take another example, and I would like to seek suggestion from you on which group should we look at next. We take a group, take it subgroup, quotient it and see what we get. So, suggestion for the next group to be considered? Real numbers, okay, it's fine. Real numbers under addition, multiplication. So, non-zero reals under multiplication, fine. Consider R star, which is a set of all non-zero real numbers under multiplication, fine. So, that is a group. Find a subgroup. Q is a subgroup, Q star. Now, what is R star quotiented with Q star? Very interesting question. What are the equivalence classes? Should be R star only? That is it isomorphic to R star? It won't be R star itself, but one can ask if it is isomorphic to R star. Firstly, we can worry about that later, but let us identify the equivalence classes. What are the equivalence classes under this quotient? So, take any equivalence class here. One, of course, one will be Q star itself, but take any other equivalence class. So, let us say consider some A Q star. For some real number, non-zero real number in R star. So, what are the elements in A Q star? See, by definition, elements of A Q star are going to be of the form A times a rational number. So, elements of A Q star therefore are all rational multiples of A. And now we quotient this out. So, that means each equivalence class represents a real number and all its rational multiples. And now we can talk about operations between different equivalence classes. What would that give us? So, each equivalence class is represented by a real number. A, we can say A represents A Q star. And if you multiply to A1, A2 two real numbers, you will get A1 times A2. Now, is A1 times A2 a different equivalence class, or can it be the same equivalence, one of the same equivalence classes? It will be a different equivalence class, because A1 and A2 cannot be rational multiples of each other. Otherwise, they would be in the same equivalence class. So, in fact, even if A1, A2 are rational multiples of each other, that is, they are the same equivalence from the same equivalence class, their product is A1, A2 times all its rational multiples. So, A1, A2 will not be a rational multiple of A1 or A2, unless A1 or A2 are rational, which means that one of the is the identity equivalence class, which is then obviously it will be the property. So, essentially in this group operation we get a subset of real numbers, such that no real number is a rational multiple of any other real number. So, we collect all such real numbers, and then just define the multiplication operation between them of real numbers, and that is the subgroup that you get. So, this is a different subgroup than R star. This is a different group than R star. We can view it as a kind of a subgroup of R star, but it's a different one because, for example, integers do not exist in this. What would happen to all integers? They are in Q star. So, they all are essentially collapsed into one single identity element, that is 1. So, all integers collapse to 1. In fact, all rational numbers collapse to 1. So, it is a strange kind of a subgroup that you get, but it is something which is not so obvious to see unless we have the quotienting operation. Here is a question. Is R star isomorphic to this quotient group product with Q star? This is not always true. For example, integers. So, for example, we know that integers are not isomorphic to 2z cross z by 2z. Why do we know this? Because z by 2z, see, this is a subgroup of z, but z by 2z is not a subgroup of z. And by definition, the product structure exists when only if you can split a group into 2 subgroups and product of 2 subgroups, essentially. So, there is no subgroup of z that is isomorphic to z by 2z. So, z is not isomorphic to z by this. At times it is, not in this case, but for certain other groups it is. Okay, let to highlight that, let us take the next example, which is somewhat less esoteric than the last one. Just consider Q star as the starting group. Q star and a subgroup of Q star, which is, let us say, all powers of 2. We had something to do with this particular subgroup earlier. Let me write this as H2 as 2 to the n in z, all positive negative powers of 2. This is a subgroup of Q star. We have seen this. Quotient Q star with this. What is this? Again, it is something you have seen. Let me go back. Okay, I had used the name H1 there, okay, and H2 was for the rest. So, I am choosing a different name, which is, I think, slightly better naming mechanism, because H2 there 2 represents all powers of 2 we are taking off. And what is the quotienting of Q star by H2? Just think, by definition, it is saying it contains all rational, each equivalence class contains all rational numbers that differ by a power of 2, by a multiple of a power of 2, essentially. So, each equivalence class can therefore be represented by a rational number which is not divisible by 2. And when I say divisible, essentially its prime factorization has no power of 2 in it, positive or negative. And this, again, that's also a subgroup. We saw that last time. There is, and then I am going to write again using slightly better notation, H2 bar. 2 bar means get rid of 2. This is set of all rational numbers A such that A is in Q star and or say A by B, sorry, A by B is in Q star, or let me better still, let me write it as AB is in Z and 2 does not divide A or B. And you see that the subgroup that you will get, the equivalence class, okay, so this is, I shouldn't write it as equal to, but it is isomorphic. Because equal, I can't really write equal because this Q star slash H2 is a collection of equivalence classes, not really a collection of numbers. But just like we can establish isomorphism in the integer case, we can establish an isomorphism between these two. And we also have, we can write Q star as isomorphic to Q star slash H2 times H2. This we saw earlier, that Q star can be split as a product of H2 and H2 bar. And H2 bar is isomorphic to Q star slash H2. So, what we have seen or learnt here is that there are distinction between groups of this kind. Earlier we saw that there are distinction between groups, either some can be split as a product of subgroups and some cannot be split as a product of subgroups. Here the same distinction is being rephrased in another terminology, which is using quotienting. That is, can we split a group as its isomorphic to being its quotient times that subgroup with which we are quotienting. Sometimes you can do this like here, sometimes you cannot do that like that. And coming back to this question, I will leave this as an assignment problem. Please work this out. You should be able to prove it both ways, that is, whichever way is correct. If it is isomorphic to this, you should be able to prove it. If it is not isomorphic, that also you should be able to prove. Okay. So, which means that quotienting sometimes gives us new groups, sometimes it does not. Like in case of Q star quotienting with H2, we do not get any new group, it is already present as a subgroup of Q star. But there are cases in for integers where we do get subgroups. So, quotienting is therefore a very interesting and very important operation. We will see its importance in subsequent lectures as well, and we will establish that this is one of the really important and fundamental operations in algebra. Now, this is its importance is further enhanced by its connection with homomorphisms. So, I actually, if you recall, I started with the homomorphism and then kind of switched to this, and the reason I switched to this was because I wanted to point out the connection, that what do homomorphisms between two groups have to say about quotienting, or what is the quotienting have to do with homomorphism. So, and the answer is very interesting. Let us consider group G, subgroup of G and quotient. So, here are three groups that we consider. Okay. Define a map from G to G slash H as phi of A is AH. That's it. Or actually this is AH may not as a name exist. So, I should make it a little more precise. Phi of H is A prime H, where A is in G and A is in A prime H. So, this map is actually a homomorphism of G onto G slash H. So, it is clear that phi is an onto map. There is for every element AH in G slash H, there is an element in G that phi maps into. So, if you have an element AH, then element A of G is certainly mapped to this. Why is this a homomorphism? Well, let us verify this. What is phi of A1 times A2? That is some A prime H such that A1 A2 is contained in A prime H, right. And what is phi of A1 dot phi of A2? This is, let us say, A double prime H such that phi of A1 is contained in, let us say, B1 H, A2 is contained in B2 H, and B1 B2 is contained in A double prime H, all by definition. A1 is contained in B1 H, A2 is contained in B2 H, and B1 B2 is contained in A double prime H. What about A1 A2? This implies that A1 is B1 H1, A2 is B2 H2, and B1 B2 is A double prime say H. This implies, I will just do this analysis, A1 A2 is A double prime H H1 H2. B1 is A1 H1 inverse, B2 is A2 H2 inverse. So, just substitute in here and you get this. No. And so, clearly this is A double prime H. So, A1 A2 is contained in A double prime H. So, if phi A1 A2 is therefore equal to phi of A1 dot phi of A2. That is the proof that phi is a homomorphism. It is not a surprise. I mean, the way phi was defined, it was essentially just using the fact we have already observed that G slash H was a group under that new operation we had defined, and it is really just that a restatement of that. So, this says that if you have a group and a quotient group, there is a homomorphism which takes a group onto G slash H, and this homomorphism really what it does is just contraction. Look at each equivalence class of G under H is contracted to one single element of G slash H. That's the map. What is more interesting is the converse. Consider any homomorphism from group G to group G hat. Now, define two sets H to be all elements A and G such that phi of A is identity, and H hat to be range of phi hat. Okay. And we have this lemma that H is a subgroup of G, and H hat, which is a range of phi, is isomorphic to the quotient group of G slash H. And this lemma tells us that essentially any homomorphism induces a quotienting of the group on which it is operating. It quotients that group with the subgroup, and the output on the range produces the quotient group. Proof. Again, very simple proof. It's just a little bit of manipulation. Why is H a subgroup of G? It's very easy to see. There is a closure property. That is, if A1 is in H and A2 is in H, then A1, A2 is in H. Because if phi of A1 is identity, phi of A2 is identity, then phi of A1, A2, by the fact that phi is a homomorphism, equals phi of A1 times phi of A2, which is identity. Then associativity, it just follows from associativity of G itself. Commutativity follows from commutativity of G itself. Identity is the that is, identity of G is also in it, because phi being a homomorphism will map an identity to an identity. Have you seen this? Why would a homomorphism always map an identity to an identity? Yeah. So, phi, it's simple. Yeah. Phi A dot E is phi A dot phi E, and which means phi A is phi A dot phi E. So, phi A can be cancelled on the both sides by multiplying with phi A inverse, and therefore, you get phi E is identity. So, identity is the same, and inverse, if A is in H, then A inverse is also in H. Why? A is in H means phi of A is identity. That means phi inverse of phi A inverse is identity, and therefore, phi of A inverse is also identity. So, that is it. So, H is a subgroup of G, and by definition of H, phi maps H to identity element. It is precisely the subgroup that is mapped to the identity element. Now, let us look at the range of phi. So, let us say let B is in range of phi. Define the set, let us say RB to be all elements of A is in G such that phi of A is B. So, collect all elements in A in G that are mapped to this element B of G hat. I want to show that this RB is one of the equivalence classes of G when quotiented with H. And for that to show, I need to just show that if A1, A2 is in RB, then A1, A2 inverse is in H. You see this trivially? So, what is phi of A1, A2? Sorry, phi of A1, A2 inverse. This is phi of A1, phi of A2 inverse. This is phi of A1 is B. What is phi of A2 inverse? Phi of A2 is B. Phi of A2 inverse is B inverse, and that is identity. So, A1, A2 inverse is in H, and that is it. That shows that all elements of G that are mapped to the element B are precisely the equivalence class, an equivalence class of G induced by H. And therefore, the range of phi, which is H hat, is an image of that G slash H. Each equivalence class is represented by one element of H hat, and the operation on the, again the same, because phi is an homomorphism, the operation on equivalence classes on the G side is mimicked by the operation on elements of H hat on the G hat side. This I am just stating, I am not writing it down. This will be a good exercise for you to go back and write it out and verify it and convince yourself. Another thing which I have skipped for homomorphism, it is again a simple fact which I would ask you to verify yourself, is if phi is a homomorphism and phi of A is B, then phi of A inverse is B inverse. Verify this. Right. So, that is the relationship between the quotienting and homomorphism. Again, it what we have proved shows that these are again different ways of viewing the same phenomenon. That you can, quotienting can be related to or connected with an homomorphism and vice versa. So, when we say we want to study quotienting of groups, we might as well say we want to study homomorphism between groups. So, that makes homomorphism also of equal importance, and again we will see later on many more applications of homomorphisms. Right? We break for today and we will meet